and 2 pi f, right? There's an alternate equation out there. Do you know what that is? It's the original equation. Yes, very good. It's omega equals to theta divided by t, okay? Why am I emphasizing on this? Because future we will come across a chapter where omega equals to 2 pi by t use korte parbo na, সবসময় theta by t use korte hobe, and then student gets confused, like we learn 2 pi by t, what is this? This is the original formula. This is the original formula, but because we are undergoing circular motion, what did we assume the angle to be? 2 pi, and the time taken to be what? T. Okay, so that's where it comes from. Anyways, that's one of the equations that we have. Our course, some very handy at the equation. V equals to omega r. What is this V? Yeah, tangential speed, instantaneous speed. But this is the velocity at which your object is actually moving, and or speed at which it's moving. This is angular speed, and that's the radius of its motion, as in where it is in its circle. Okay. So yeah, this is the recap of what we have done. Okay, so right then, last class we looked into what is the requirement for circular motion. So circular motion, you know, we found that if your object is going in a particular direction, right, and you apply force in that direction, the object's velocity will increase, but there won't be any change in what the direction. Okay. Now, if you apply a force at an angle, then one component of the force will actually make your object go faster, and the other component can't make it go faster or slower, but it will change something though. What is it? Direction, right? So as a consequence, what will happen is your object will actually turn. And we found that if you want to make an object change direction, you need to apply a force that is not what to the motion. If you want to make an object, right, turn, you must apply a force that is not what to the motion. Parallel, okay? Because if you apply a force that's in parallel to the motion, it can't change direction. It can only make it go faster or slower. If there's any angle that's creating a vertical component, right, that will change your direction. So we found that if you apply a force at an angle, your object changes direction. So we have seen that. Then the object will continue to go in its original path. It is of Newton's first law. What does first law state? That if you apply a force on an object, momentarily, it will change direction. But will it continuously change direction, or will it then continue to go in its original path? Original path, right? So imagine there is a car going like that, and or anything, a ball, and you hit the ball, it turns. Does it keep turning, or just go the direction there? It'll just go there, right? So for circular motion, what do we want? We want it to change direction all the time. And if you want an object to change direction all the time, you must apply force all the time, right? So eventually we found that if you want to achieve circular motion, this is what you need. The object needs to have what? Forward velocity. This is very important, okay? So it has to be moving. You can't create circular motion from a stationary object. And you need to apply a force that is what to this velocity? Perpendicular. What is the consequence of these two? So the consequence of these two is that the object's magnitude of velocity will remain the same. So if the object comes to this location, right here, you'll find that the velocity is still the same, okay? So if you V hoy, you'll find this is also V. However, because the force is acting perpendicular, what does the object only do? Change direction, right? And if I can apply force at every given instance imaginable, right, what will the object continuously do? Change direction. And that continuous change in direction will eventually, once adds up, right, become a what motion? Circular motion. Even for the brief moment, right, if you let go of the force, what would the circle become? Yeah, it won't be a circle anymore. It'll get distorted. Okay, so I'm going to do the force zero dicho, and I stop force. It'll just continue to go that way. Okay, so imagine there's an object going in a circle. The moment you stop the force, it'll just continue to go that way. Okay, the normal misconception out there is that force to the bondage, the object will slowly come to a stop like a fan. That's not true. Okay, so if normal objects undergoing circular motion, if you get rid of the force, they'll just fly off at a time. Okay, so yeah, that's what we have seen so far. So the question is, what is the requirement for circular motion? 4 marks এর জন্য আসে এটা, by the way, different chapters আসে. Different chapters মানে হচ্ছে there are like 8 different chapters where the same question comes, but you have to apply context. Do you understand what it means by context? So the questions would be based on, let's say, particle physics. You have to introduce particle physics into your answer. The because the force that's been applied there is going to be different in different chapters. Okay, so yeah, the thing that we'll be looking into is what is the requirement for okay, I'll first explain and I'll give the answer. So shall I to screen it once again? We start the answer with an object that's already undergoing circular motion. Okay, so let's say an object is already undergoing circular motion, and you need to explain what is needed for this object to attain and achieve and retain circular motion. মানে হচ্ছে continue যদি করতে হয়. So let's try to see what's going on here. So you have your object here, and it's moving in a circle. First thing, can you tell me what's the first observation you can make when looking at this motion? Huh? Concentrate actually বলা possible না because আমার হাত তো হচ্ছে evenly যাচ্ছে না. So আমি যা করতেছি এটা দেখে what is the conclusion that you guys can come across? Okay, that's one of them. আর কিছু? The most obvious one. Let's say you're grade 7 physics students, right? তোমাকে জিজ্ঞেস করে what is this ball doing? What would you say? Moving in a circle. আচ্ছা, and in order to move in a circle, what does it need to do? No, you guys are going ahead of the basics. The first thing that you notice here is it's changing what? Direction. So that's the most obvious thing. It's a perfect circle, draw across the circle, right? Let's say this wasn't there, and I asked you what is this doing, right? Keep this changing direction, right? So the first thing you need to come across is that changes direction. So your object here is continuously changing direction. So it's going this way, and then after a bit, it's here. So its direction has changed. It's going somewhere else. Now, if there's a change in direction over time, right? What can we say the object experiences? Acceleration, right? But because it's changing direction, a particular quantity is changing, velocity, right? So this velocity that you have here and that velocity that you have there might be same in magnitude, but they're actually different because velocity also accounts for what of the object? Direction, right? So there's a change in direction that causes change in velocity. Are you clear so far? Okay, now the change in velocity has obviously taken over time, right? So whenever you have change in velocity over time, what is exerted or what is experienced? Acceleration, right? So right now, what we can come to a conclusion here is that this red object that you see here is actually what? Accelerating, okay? So this is accelerating. Now the question is, if it's accelerating according to Newton's second law, for acceleration to take place, there must be, right? There must be something acting on it. What is it? A resultant force. That's very important. You have to say net force because force is not enough. Force can act on many objects, right? So the table in front of you, is there force acting on it? Yes, there's weight, there's reaction, right? Probably your hand is applying a force on it. Is it accelerating? No, why not? Yeah, the net force is 0. This is accelerating, right? So there must be a net force. So this object here should be experiencing a resultant force here. So now the question is, which way should the resultant force be acting? So there must be a force acting here. And so the answer, if you just end it here, it's fine. You said that the object is continuously changing direction. Because of that, there's a change in velocity. And because of change in velocity over time, it experiences an acceleration. To provide that acceleration, what is needed? A force. And what do we call that force? The centripetal force, right? Now, further, Judy, that force has to act which way for this to be possible? Towards the center, because we need our force to be what to the direction of motion? Perpendicular. And as it turns out, mathematically, if you have an object moving at a tangent, and if there's something perpendicular to it, it will always pass to the what of that circle? Center, right? So eventually, centripetal force has to be a force that acts towards the what of a circle? Center of a circle, okay? So yeah, this is the requirement for circular motion, that there must be a force acting towards the center of the circle, and we call it the centripetal force. Okay, so 4 marks, what is the marking scheme here? What do they ask for? But do you have any question? What if the force changes? Can you tell me what kind of a circular motion will I have? Great. My force to fluctuate yeah, so you'll find that it's also fluctuating. It'll form like a very random shape, right? It'll try to be in a circle. Force to the barad though, will it form a tighter circle or a loose circle? Tight, because if you apply more force, wouldn't it move towards the center more, right? And if you release the force, it will start to go outwards. So if your force fluctuates, you'll notice that the object does like a flower-like pattern, depending on how you vary your force. Okay, so yeah, that is the requirement here. So 4 marks unit ashe. Always remember your answer has to be with context. Okay, আমি যেটা দিচ্ছি এখানে, this is just a template, right? Exam এ যা জিজ্ঞেস করে ওটাকে use করে answer টা করবা. So just keep that in mind. So yeah, when an object in circular motion is undergoing continuous change in direction, this change in direction leads to a change in velocity. The change in velocity takes place over time and results in an acceleration. To provide this acceleration, a force is needed acting towards the center of the circle, known as the centripetal force. Yes, we're going to do that right now. So centrifugal force is not really a force. It's actually a name given to a type of force. Are you guys done? Okay, so what do we do now? So the thing that we need to clarify first is what is centrifugal force in different scenarios. So I'll give you examples of circular motion, right? You need to figure out what provides centrifugal force in that scenario. So এটা হয়ে গেলে বলো, I'm going to show you something very important. Done, সবার? আচ্ছা, একটু এদিকে দেখো. Let me explain. So centrifugal force is really not a name of a force. So before I start, can you tell me what are the four forces of the universe? There are only four forces. What are those? Weak nuclear, strong nuclear, gravitational force, and electromagnetic. So electromagnetic interact component is electrostatic. Okay, so basically static and magnetic together, right? So whenever you have an object undergoing circular motion, right, it has to be one of these four, because centrifugal force is not the name of a force. It's the name of a type of force. I'll give you a simple example of this. Do you know what is a resistive force? What is it? Something that opposite to you, right? Slows you down. Can you give me examples of resistive force? Air resistance, contact friction, viscous drag, like when you're going through water. So these are all types of resistive forces, right? So as a general, we call them resistive force. Similarly, centrifugal force is like an umbrella term. There could be any force under that name, right? As long as that force helps you undergo what motion? Circular motion. Okay, so let's see the different types out there. So these are examples and applications of centrifugal force. Okay, screen it to কিছু just বুঝার চেষ্টা করো. So the first one is a rock that is spun in a circle. So like the rock কে নিয়ে হচ্ছে, you're spinning this in a circle. Did I mention what kind of circle this is? I think I did last class. Yeah, it's called a horizontal circle. Okay, so it's essentially there's a rope here, and a rope is tied to a ball at the end there, and that ball is made to spin with this rope here. So that's the scenario. So you need to figure out in this question what provides centrifugal force. So first of all, to clarify, Corey, there's a force acting towards the center. Do you agree? Because it's undergoing circular motion. What do you call that force? Centrifugal force, right? So there's a force out there, it's called centrifugal force. Now that centrifugal force that you see here must be provided by something in real life. What is there in this rope that provides a force towards the center? Tension. Okay, so in this scenario, in this example, what provides centrifugal force? Tension. Okay, do you understand what I'm trying to do right now? So we need to, I'll give you examples, but we need to figure out in each example what provides that centrifugal force. Okay, so এখানে হচ্ছে এক্সাম্পলটার মধ্যে হচ্ছে when a rope is spun in a horizontal circle. Can you guys predict it? It's difficult হবে, but দেখি পারো নাকি? Vertical circle কি হবে? The centrifugal force. Yeah, so when you do a vertical circle, right, there's a force that's helping you sometimes. What is that force? Gravity. But sometimes it's actually opposing you. So when it's opposing you, who has to play the main role? Tension. And when it's assisting you, the tension doesn't need to really take the main stage. Weight টা কাজ করতে পারে. And sometimes weight does too much. And I'll give you an example of this. Imagine you have a very heavy rock, right? And you're spinning in a circle and you're not spinning fast enough. Rockta ki korte pare bolte parba? Just try to imagine you have a very heavy rock tied to a rope and you spin it, it goes up, right? But you slow down. As you slow down, what will the rock do? Yeah, you'll find that at one point it just goes and then falls, right? That's because what was too much? Weight. And then the velocity you had was not enough to keep it in the circle. Okay? Can be fast enough how then you can overcome the pull of the gravity and continue to go in a circle. That's what we're going to see today. Okay, circular motion is basically trying to fight that gravitational pull out there and stay in a circle. Okay, so yeah, when a rope is spun horizontal, the tension provides what? Provides the centripetal force. That's how you phrase it. Okay, so tension to provide korteche, but it's providing the force that's needed to go in a circle. So that. Are you clear about the example? So I'll give you more questions right now. So number two, so number one was that. Number two is conical pendulum. Conical pendulum is very popular in your syllabus. What's a conical pendulum? I'll try to show one here. I don't have a mass, unfortunately. Conical pendulum is this. So you have your typical pendulum out there. This is a rope, right? You have your typical pendulum, which will do what? Back and forth like that. That's called a simple pendulum. We have this in our oscillation chapter. So it just go back and forth in what plane? A single plane. Like, plane mane buchho te je straight jaচ্ছে. Conical pendulum is this. Do you see that? So if you look at the base that's forming here, isn't it a circle? And if you try to take the rope and see what shape it forms, doesn't it form a cone? Right? So that's a conical pendulum. So you take a rope, right? You attach your mass at the bottom of the rope, and then you make the rope go in a circle. Here we have it. So as it goes in a circle, it does produce a circular motion with the bob at the bottom, right? But it forms at the bottom. So what kind of pendulum is this? It's called a conical pendulum. I hope you understand the 3D nature of it. So this is your conical pendulum, and this is the path it takes at the bottom. Can you tell me what provides centripetal force here? Weight and no. As an AA student, it not part embarrassing. What provides my centripetal force in this scenario, the conical pendulum? This is the path taken. This is the mass. Huh? Component of? Which component? Yes, very good. Okay. So I'm বলি কি হচ্ছে এখানে আমি আগেও বলছিলাম you have to bring your AS components ideas here as well. Okay, সব জায়গায় আসবে. So if you look at this tension in the rope, this tension in the rope can be broken down into two components, right? And a conical pendulum হচ্ছে এখানে একটা angle generate করা হয়. If you have an angle here, obviously এটা math করতে লাগবে, but I want you to understand the whole thing because eventually আমরা শিখতে হবে. So this is my angle theta here. Can you tell me the tension that you see in the rope can be broken down into what? Two components. What would the components be? That angle that I've drawn here is a theta, right? So what should the components be? T sine theta and cos theta, right? So one of them will be acting vertically upwards here, and another component would be acting horizontally like that, right? Which one is T? Sorry, which one is T sine theta? Yes. So this one that you see here, this is T sine theta, and what's the vertical one? T cos theta. For circular motion, your force has to act to which point of the circle? Center. Which force here acts towards the center of the circle? T sine theta. Okay. Sometimes students will go like, but this looks like the center of the circle, and this should be the answer, right? But that would have happened if my object underwent a what circular motion? Vertical circular motion, which will come back later on. Right now, the bottom is the circle. So you need to find the force acting towards the center of the bottom. And that would be your horizontal component of tension. Okay, so that's the answer in this case. So for a conical pendulum, the force is horizontal component of tension. Okay, so let's go into other examples. Are you clear about these two? And are you trying to get a hang of what I'm trying to do here? So I'll give you random examples out there, and you need to figure out what provides my centripetal force. Because once you do that, it opens up the gateway for everything else. So if force যদি বের করতে পারো তুমি acceleration পাবা, velocity পাবা, time পাবা, সবকিছু পাবা। Force টা বের করতে হবে, okay? Right, next is I'll give you progressively complicated questions, so it আগেরটা থেকে আর একটু complicated. So an aeroplane. So this is an aeroplane that's taking a turn and going in a circle. Okay, you need to figure out what's the centripetal force here. So this is an aeroplane undergoing circle. I mean, to arc a diagram there because students usually get confused with this diagram. If you look at the aeroplane's path from the top, right, top view to the day, this is the top view. Your aeroplane is here. So that's where the plane is. And it's undergoing a what motion? Circular motion, like that. So it's just going in a circle. Okay, so you need to figure out what the force is needed for this plane to go in a circle. Our number 4 is very common, but it's very complicated as well. A car going in a circle. So what are the forces that are needed for a car to maintain circular motion? Okay, around a roundabout, by the way, perfect circle করতেছে. Right, so there you go. Think about it. I mean, জিজ্ঞেস করো সবাইকে আলাদা করে. So what your opinion is? So same thing. It's a plane going in a circle, and নিচেরটা হচ্ছে a car going in a circle. And 5 হচ্ছে আরেকটা ওটা পরে দেখাচ্ছি। এই দুটো পারলে you can answer that. So yeah, what do you think is the one for a plane? কেউ কি answer করতে পারবা? Plane circle যখন যায়, planes do go in a circle. It's a very common pattern they take sometimes. ধরো land করতে হবে, and the airport is not free, right? So they'll just keep going in circles. Just continue circle করতে থাকবে, তারপর যখন হচ্ছে runway clear থাকে, they'll just land, right? So how does a plane go in a circle? There must be a force acting towards the center of that circle, right? Plane যদি forces imagine করো, forward force, thrust, backward force, air resistance, upward force, lift, downward force, weight. What's the force to the side? Component of weight. Lift and air resistance. It's something to do with lift, not air resistance. So how the lift? Vary the lift. Component of lift, but lift is acting upwards, right? How can you have a component of something that's vertical? Yeah, but here to our tension angle, na? So if something's at an angle, I can break it down, right? So how do I do that here? Oh no, they manipulate access to the reality I manipulate for them. Yes. Yes, right. Okay, so there's something missing here. This plane can never turn, the one I've drawn right now. And if you've been in a plane that actually after takeoff you have to be turn for it, right, to get into their path, you'll find they start to what? Tilt. They do tilt a lot, okay? Tilt cannot correct. They're tilting because they're trying to take what? A turn. And when they tilt, see what happens? This is the force that keeps the plane flying. It's called the lift, right? A lift, যখন tilt করা হয়, creates a what with the vertical angle, right? And suddenly your lift can now be broken down into two parts. Ekta hocche edike, what is that going to be? Eta jodi L hoy, L ki hobe eta? Sin theta, correct? And this one is very important, by the way. Etake ignore korbo na amra. This is also going to be a component. What is that component going to be? L cos theta, right? So this is the vertical component here, which is going to be L cos theta. The L cos theta is there for what? To keep your plane up. Karnal the plane pore jabe, right? And the L sin theta is there to keep your plane in what? Turning, right? So you'll find that fighter planes, right? Fighter jets or planes that can maneuver very easily. Or they go turn kore, right? They go almost sideways. It's very common that planes will just go like fighter jets, they go sideways. Because if they go sideways, they can use এটা যদি আমার lift হয়, right? So that's normal plane. If I go like that, like angle create হচ্ছে না, if I go all the way that way, isn't my lift entirely becoming the centripetal force, which means they can turn very quickly. Main problem with planes হচ্ছে the component is very low. And so when a normal plane takes a turn, right? Do you know how far they actually go to make a turn? Half of Bangladesh. Some of the planes, they half of Bangladesh, they go all the way to like end of Gazipur and all the way there just to land in Uttara, because their angles can maintain korte hoy. They can't do a lot of turn because passengers থাকে ভিতরে, right? So they'll do এটাকে banking বলা হয়, by the way. The term is called banking. ওই bank যখন করে প্লেনটা 5 degree 10 degree করে, but because they can't bank much, what is the sacrifice they make? It has to be a very long circle, okay? If they bank a lot, they can do a small circle. So the bank korle key advantage, they can use their lift more for turning, but that becomes uncomfortable for passengers, so tar jonno kore na, okay? So yeah, that's the idea. That's how planes actually turn. So এটা আমি draw করে দিচ্ছি আরো একটু better করে. What about a car? How does a car turn? গাড়ির আবার তো কোনো banking বলে কিছু নাই. So if a car top view দেখো এখান থেকে, right? And this is a car that's moving forward. This is the front of the car. And the car turns this way. What turns the car? Friction. So a normal car will have friction forwards, friction backwards, reaction force upwards, and weight downwards. What's the sideways force? The tires tilted. Okay, but contact force. I mean, eventually it will have to be one of the four forces, right? But can you tell me in particular where is the force originating from here? আচ্ছা আমি দেখাই, তোমাদের অ্যান্সার যেটা বলছো এটা এক্সামে দিলে মার্ক দিত, but it is a little bit more complicated than just contact force. Let me explain. It's obviously from the tires, right? And এটা is coming from the fact that the tires are actually trying to go outwards. So imagine your car tire is this, right? This is the front tire, and your car has to take a turn right now. So যেটা করবে ওই wheel and everything, steering wheel turn করতেছে and whatnot, the car is actually trying to go forwards because of what law? Newton's first law. Because an object continuing to go forwards will try to go forwards unless a force acts on it, right? So once it tries to go forwards, what happens is this tire that you see here pushes the road outwards. This is trying to go outwards. And then the road pushes the tire inwards. And that force that you see here, that is your centripetal force, which is actually friction. Or contact force, whatever, but the contact force here is friction. Now, student data bujhe na, and it is actually normal. So I'll explain with a better example. Imagine yourself in a car. Acha, you're inside the car, you're in the back seat. Our gari back seat ta hocche ekdom polished, flat at the surface, like a steel surface, and you're sitting in the back seat of your car, and the car turns, right? What's your natural understanding of what your body will do? As the car turns, do you turn with the car? Or do you start to go the other way? The other way, right? You're like, shifting the other way. Why? Because you're actually not going the other way. You're actually going the original way. So you have moved outwards. And as you start to move outwards in normal cars, right? Is the seat polished or anything? No, right? What is it? It's actually made of a very rough material. In fact, it's like a bucket shape. Being a bucket means that if you try to move, what does the seat apply on you? Friction. And then it keeps you going inwards. Sometimes if your car turns too fast, right, friction is not enough. That's when you go and hit the watt of the car, like a door, and the door will push you in. In some cases, you'll find that they're like ওই যে কোট হ্যাঙ্গার থাকে না, ওইটা হাত দিয়ে ধরতে হয়। বাসে হয়। So বাসে তো you don't have a seat, and imagine one of those airport buses where like there's no seat, it's quite empty, right? There are a lot of these things that you have to hold on to, because when the bus is turning, your body doesn't have any centrifugal force provided. So how do you gain the centrifugal force? With your arm. So you hold onto the pole, and the pole brings you back in. You fall the other way. Okay, so this is actually what's happening with the tire. The tires are actually trying to go which way? Outwards. But what keeps them in? Friction. And that's the reason why rainy days, car crashes are so common. Why? Because when you try to turn, you're relying on what to provide you friction? The road. But the road is slippery, right? And there's not enough friction. So eventually, you go off the track. Okay, so that's why on a slippery road, it's very difficult to take a turn. Right, so that's for a car. This is for your aeroplane. One last example, এটা হচ্ছে, এগুলো একটু কপি করে না, আমি ডিসক্রিপশন গুলো দিয়ে দিচ্ছি, বাট প্লেন আর কার এই দুটো হচ্ছে গেস করা খুব ডিফিকাল্ট, তার জন্য আগে থেকে দিয়ে দিলাম। There's one more that I want to share with you guys. আচ্ছা, এটা অ্যান্সার করে না, তারপর একসাথে সব করি আমরা। Can you tell me what is this person doing? Yeah, so motorcycle is taking a turn. Why does he have to get on his knees? They do this, right? ওদের নির মধ্যে প্যাডস থেকে, when they turn they go sideways almost, right? এই যে এভাবে করে টার্ন করে কেন? Yeah, so if you are in a bike, right, and if you try to take a turn, keeping your bike upright, it will never turn. If you ride a bicycle, they go from body till 40 of it. Cannot, because when you have a bike tire that's upright like that, there's absolutely no force, or there's not enough force acting which way? Towards the center. How can you create more force towards the center? So what you do is you tilt the bike. As you tilt the bike, isn't this tire now pushing the ground more outwards? Tire that you tilt for, isn't it pushing it outwards more? As it pushes it outwards more, what does the road do? Push it inwards even more. So if you look here, ওরা কিন্তু mainly tire টার উপরে focus করতে হয় এখানে. So if you look at the tire here, do you see how the tire is at this moment? It goes to an inclination of around 30 degrees to the ground, which is very tilted, by the way. Okay, so এই অ্যাঙ্গেলটাতে টায়ার থাকে. So if I told you that there's a motorcycle taking a turn and the tire looks like that, most people won't believe that. Motorcycle পড়ে গেছে, right? But do you see that this is what you need to be in order to turn? Why is that so? If you do that, you have the greatest what outside? Push. And as a result, you'll have the greatest reaction inside. Or reaction থেকে use করা হয়. Okay, component of weight অনেকে মনে করে is actually a crucial factor here. It isn't. Okay, যে তার ওয়েটটা ইউজ করতেছে to turn, it's actually the tires. এই টায়ার্স গুলো কিন্তু অনেক হাই গ্রিপ, they don't slip. Okay, so এই যে টায়ারটা যখন এরকম হয়ে যায়, they're pushing the road the greatest. এখানে বোঝা যাবে না, but let me show you. এই কন্ট্যাক্টটা কিন্তু এইখানে সবচেয়ে বেশি. Where would you have more contact? A tire that's upright or a tire that's tilted? Tilted actually. I know আমার ডায়াগ্রামে দেখে মনে হচ্ছে যে এখানে কন্ট্যাক্ট কমে গেছে এই জায়গাটা, because I have not drawn like a 3D version of it, but এখানে কিন্তু the tire is more in contact with the ground. This is tilted. This is grazing the ground more. So therefore, there's more what on this tire? Friction outwards, is trying to go outwards, and as a result, as a consequence, the road is pushing it further inwards. Okay, so this is the outward force here, and there's the inward force there. So at the end of the day, they're all friction, but it's how you manipulate that friction that's important. Okay, so yeah, these are the examples out there. Copy for now, at least the aeroplane and the car, I need to copy for. The car one. Okay, I'll explain the car one more time. So we'll do this separately here. This is the car going forwards. Right. So the car's actual path is supposed to be this. Okay. So actual path is supposed to be this one. I'll just do another version. Right. So the car is supposed to go this way because everything tries to move in a straight line, right? But the car doesn't actually go that way. The car actually turns and goes this way. That's the path taken, right? So the car was originally trying to go forwards, but then it goes this way, right? So it was actually trying to go out of the track. So imagine you're a passenger inside this car. You're here, right? When the car takes a turn, and let's say it's a slippery seat, there's no friction out there. Where do you expect yourself to be? এই যে ধরো তুমি প্যাসেঞ্জারতে যেই জায়গাটায়, right? And গাড়িটা turn নিল। এই ডায়াগ্রামের মধ্যে the one here, right? Where do you expect yourself to be? Far right or same position compared to the previous diagram? Yeah, it's actually same position. But with the context of the car, you feel you're moved which way? To the right. Because look at the passenger. The passenger was here, right? And passenger the গাড়ির center seat চলে গেল না? Do you get my point? So the idea is that you feel you're moving outwards, but you're not moving outwards. What's moving inwards? The car. Okay. So ওই inwards movement যেটা হচ্ছে ওটা টায়ারটা গাড়িটাকে ভিতর দিকে push করতেছে, and you start to go outwards, or you appear to go outwards, and then eventually what brings you in? The seat, the cushion, the doors, and everything else will apply a force on you inwards. Okay. So yeah, if your car takes a very slow turn, right, you wouldn't really feel much, because the friction is enough. But when a car takes a very hard turn, the seat is not enough. You need to take assistance from the door, or you have to hold on to something. Okay. Right. So that is it. There's just one bonus question out here. It's the easiest. But I'll start a conversation that next class is important. This thing that you see here, it's a path taken by an electron. Okay, so there's an electron here. And what's at the center of this structure? Nucleus, right? So right at the center is your nucleus, which is like 1,000 times smaller. So the electron is undergoing circular motion like that. Do you agree? No. Okay, who doesn't agree? Right. This is the velocity of the electron and everything. This is the path of the electron. Can you tell me what is the force that keeps the electron in its orbit? Yeah, electrostatic force, because the electron is what? Negative. And what is the nucleus? Positive, because of the protons. And there's actually a force exerted towards the center, which is your centripetal force. And that is just plain simple what force? Electrostatic force. Okay. এখন question যেটা হচ্ছে, we have time today, but let me start that process. Your electron and your nucleus, right, are oppositely charged. And according to electrostatics, opposite charges attract each other. Why is the electron not crashing into the nucleus? So if you keep moving, you don't crash. Maintaining something. Anyone else? Question I mean, it's a classic simple example out there. Your nucleus is positive, your electron is negative. But then, this is the first thing you have asked whenever you heard of an atom, that why aren't the electrons all like sticking to the nucleus? Because the electrons are negative and the nucleus is very positive, right? In like gold case, cello plus 90 protons, right? That's very positive. So shouldn't the electrons just come and crash into the nucleus and like surround it? What keeps them up there? Same goes with planets and our sun. So our sun is the center, and it's pulling the planets, but the planets are going in a circle. They're not crashing into it. But there are things that crash into the sun, like asteroids and comets and stuff like that, right? So what's keeping the planets from crashing into the sun? Same answer goes here as well. Inertia, what was it? Constant velocity trying to go outwards. Do you have an answer? Yes. So the objects that fail to be in a circle, what do they lack? The tangential speed. Acha, okay, I'm believing in there's this example out there. It's called the Newton's cannon. Ask you to start with Nishta. So Newton's cannon is a thought experiment, a very famous thought experiment. Next class, I'll show you the animation of it. But the experiment goes something like this. Screen it. Newton struggled with circular motion. That's why eventually he failed at it. That's the reason why Newton's laws are not used in explaining planetary orbits. There's someone else's law called Kepler. Okay, so what did Newton try to do here? So Newton came up with this idea here, which is called the Newton's cannon. Newton's cannon key, actually. So he imagined that at the top of the Earth, there's this massive cannon out there. Cannon which fires a shell, right? And he said that he'll fire a shell out of this cannon at a velocity. And because gravity is acting, right, what would this shell do? Go forward? Not to use fire a bullet or anything. What does it do? Is it goes forward? Not though. Yeah, it goes in a parabola. It goes downwards and forwards, right? So it'll do. I was looking for the word projectile, but anyways. So yeah, it follows a projectile path, right? So niche pore gelo. So Newton thought, acha, what if I increase speed? And you guys know this very well. If you increase velocity, what increases of projectile motion? The range. Anyways, it's called range. So the range increases, right? So the range very low. And he said that let's keep increasing because it's hypothetical term. So he kept increasing, and while doing this math, by increasing, he came across a very interesting phenomenon. What he found was that there is actually a speed at which you fire the cannon, right? The cannon will go like that and go very far and then eventually fall and hit the ground, okay? But if you keep increasing the speed, it'll keep going further before who overcomes it? Gravity. মানে বুঝছো তো দূরে দূরে যায় পড়তেছে তো যত বেশি স্পিড দিবা তত বেশি রেঞ্জ আসবে but eventually it'll go and hit the ground, right? And while doing his math, he found that there's actually a velocity at which you fire it that it'll keep going like that, and before it can fall back, where does it come back again? To the start. And what does it do then again? It repeats the process and it gets stuck in this thing that we now know as the orbit. And that's how satellites stay out there. That's how electrons stay out there. That's how anything will stay out there as long as they have the right what? Speed, orbital speed. That's why satellite যখন send করা হয়, a very common misconception out there is that rockets এভাবে যাবে, satellite কে দিয়ে তারপর they'll come back. That's not what they do. The rockets actually go into the orbit. That's where the speed comes from. Rocket taking the speed নিয়ে enter করে, and then they release that satellite. So the satellite is also at the same speed, and then the rocket comes back. So rockets actually do this. And on the top of their orbit, what do? They release the satellite and they come back. And the satellite now has the right speed to remain where? In orbit. And they continue to be there forever. Okay? Unless or until what happens? Some force acts on them. Okay? So yeah, this is how objects maintain their orbit. Same goes with your electron as well. Electron just has the right speed to be in the orbit. Okay? It is experiencing a force inwards, but enough to stay in this orbit. Okay? So yeah, anyways, I'll go through this again next class.